Have you ever wondered about the composition of the universe and why it's mostly matter and not antimatter? Imagine a cosmic scale where matter and antimatter sit on opposite sides. You'd expect a balance, right? But surprisingly, that's not what we see. Our universe is dominated by matter, with very little antimatter in sight. So, what are matter and antimatter, you may ask? Essentially, they're twins, identical in most properties, yet bearing opposite charges. Like rival siblings, when they meet, they annihilate each other, releasing an enormous amount of energy. However, the question that baffles physicists and cosmologists alike is this: if the Big Bang should have birthed equal amounts of these twins, why do we see a universe that's predominantly matter? This riddle has led us to the concept of matter-antimatter asymmetry, a captivating puzzle piece in the grand cosmic jigsaw. In this video, we explore the concept of matter-antimatter asymmetry, a fascinating topic in the realm of physics. Matter and antimatter, while similar, have opposite charges. But what happens when they meet? Well, they perform a cosmic dance, a dance of annihilation. Imagine two partners, identical in every way but one, their charges. When they come together, they don't merge or combine, but annihilate, disappearing in a flash of energy. This is the dance of matter and antimatter. Now, let's travel back in time to the moment of the Big Bang. Picture a cosmic kitchen with a recipe that calls for equal parts of matter and antimatter. If the universe followed this recipe, every particle of matter should have found an antimatter partner, leading to a grand cosmic dance and ultimately mutual annihilation. But glance around, look at the stars, the galaxies, the planets. Our universe is far from empty. It's brimming with matter, while antimatter seems to have disappeared from the dance floor. This begs the question, why is our universe dominated by matter? Why didn't everything annihilate? Perhaps the universe cheated on the recipe, making a little more matter than antimatter. Or maybe something happened after the Big Bang that tipped the scales in favor of matter. It's one of the biggest mysteries in cosmology, one that brings us face to face with the limits of our understanding. This tantalizing puzzle is not just a question of cosmic proportions, but also a deep paradox that challenges our understanding of the fundamental laws of physics. It's not just about what's out there, in the vast expanse of the cosmos, but also about what's in here, in the world of particles and forces. The answer to this riddle might lie in an intriguing concept called Charge-Parity Violation. This idea suggests that the laws of physics might not be the same for matter and antimatter, leading to a slight preference for matter. It's a bold idea, one that could rewrite the rules of the cosmic dance and possibly solve the mystery of our matter-filled universe. Charge parity, or CP violation, is a process where certain laws of physics aren't identical when particles swap with their antiparticles and their spatial coordinates invert. Now let's delve into this concept a bit more. Imagine a mirror world where left is right, up is down, and matter is replaced by antimatter. This is a reflection of our reality, a parity transformation. Now, if we flip the charges as well, swapping positive for negative and vice versa, we get a charge parity transformation. The intriguing part is, if our universe and its laws of physics are truly symmetrical, then the behavior of particles in our world should match their counterparts in this reflected, charge-flipped world. But here's the twist: they don't. This discrepancy is what we refer to as CP violation. It's like a cosmic sleight of hand, a tiny but crucial asymmetry that could explain why there's more matter than antimatter in the universe. But how do we know this? Well, it's all thanks to subatomic particles called B-mesons. B-mesons are interesting because they oscillate between their matter and antimatter states, making them perfect for studying CP violation. In fact, experiments like the Belle at SLAC and the Belle in Japan have provided us with valuable data indicating CP violation in B-meson decays. These experiments observed that B-mesons and their antimatter equivalents decay at slightly different rates. It's a subtle difference, but it's enough to suggest that our universe doesn't treat matter and antimatter quite the same. This tiny imbalance could have tipped the cosmic scales in favor of matter over antimatter, shaping the universe as we know it. These findings could potentially unlock the mystery of why our universe is primarily composed of matter. It's a tantalizing glimpse into the asymmetrical dance of the cosmos, a step closer to understanding the grand tapestry of our existence. Matter-antimatter asymmetry is one of the great unresolved mysteries in physics. This puzzle, left unanswered, not only questions our understanding of the universe's composition, but also poses a challenge to our comprehension of the fundamental laws governing reality. To start, let's ponder the significance of this asymmetry. The universe, as we know it, is predominantly matter. Yet our current theories suggest that the Big Bang should have birthed equal amounts of matter and antimatter. So, where's all the antimatter? This question isn't just about tallying cosmic inventory. It's about understanding why the universe exists as it does. It's about unraveling the story of creation itself. Now consider the implications of this asymmetry. Should we solve this mystery, we could potentially unlock new physics beyond the Standard Model. The Standard Model, though incredibly successful in explaining the world of particles, is not complete. It doesn't account for gravity, dark matter, or dark energy. Could the anomaly of matter-antimatter asymmetry provide a gateway to these uncharted territories? Could it be the missing link that reconciles the quantum world with the cosmos? The possibilities are as vast as the universe itself. Furthermore, this asymmetry could shed light on other fundamental questions. Take dark matter, for instance. This elusive substance, detectable only through its gravitational effects, makes up about 5/6 of the universe's matter. Yet its nature remains a puzzle. Could the matter-antimatter asymmetry be the key to understanding what dark matter is? Or could it provide clues about the universe's origin? These are questions that continue to fuel the curiosity of physicists and cosmologists worldwide. As we continue to explore this fascinating concept, we inch closer to understanding the very fabric of our cosmos. The universe is full of mysteries, and matter-antimatter asymmetry is one of the most intriguing ones. And as we delve deeper into this enigma, we realize that the quest for knowledge is an eternal journey, ever leading us towards new horizons of understanding.